Hello everyone, my name is Kamyar and I just got here. I had to run here, so I'm still breathing. So I'm going to talk about the joint work I have done with Emma and Anima like almost a year ago, and called Bayesian Deep Q network, in short like BDQN, which is a kind of study of like Thompson sampling based exploitation in function approximation setting in the value-based setting. Okay. So since this function approximation setting, I'm gonna approximate the Q function as a linear transformation of the feature representation of states. And the way I learned this Q function is using is like feeding the Q function to the target value, which is the reward of the next time step, and max, gamma times max of like the Q at next time steps. Okay, so this is the way I'm gonna learn my Q function. And since I'm using the linear approximation, the thing I'm gonna feed is gonna be feeding that linear model to this target value. Okay, so how I get this this feature representation is using a neural network. This neural network is the same neural network people use for, this is exactly the thing you have in DQN, except I just removed the last layer to get my feature. So my feature is gonna be the output of this network, which is like DQN network, except the last layer is got removed. So this is gonna give me feature representation, and given the experiences I got so far, like times the current state, current action, the current reward, and next state, I'm gonna feed this Q function to the target, and I'm using, instead of using the same Q, I'm using target Q. And again, since it's a function approximation, I'm gonna feed that linear model to this target, which is like, so far is everything is DQN. I'm not saying anything further than DQN. And in order to learn this Q function or this linear model, I'm solving this regression problem, okay? So I'm solving this regression problem. I'm solving for theta and W, and for the exploration I use epsilon greedy to get like exploration. Let's assume that at some state I have like six actions, and like red, blue dots or diamonds, they are like the estimated Q value that this regression problem gave me, which is gonna give me a point estimate. And let's assume that the red cross are the actual value of the Q function, and someone gave me the confidence I have over each action. This confidence might be like, let's assume that is given, okay? What's gonna happen if I do epsilon greedy, I'm gonna go with the first action with probability 1 minus epsilon and randomize over all the other actions, no matter what is the confidence and how good are the other actions, okay? So let's assume that I'm going for, in the coffee break, I'm going to get coffee. The first action is latte, second is like cappuccino, the third one, I don't know, is iced latte, whatever. And the fifth one, let's assume, is like vodka in the morning. So if you know that with probability 1 minus epsilon, if you want to go with the first action, you should not randomize vodka with the same probability as you do randomize for cappuccino, okay? So if I had this confidence, what I could use, I think I missed like In's talk, but I guess he said you can fit a Gaussian. Let's assume I'm going to fit a Gaussian distribution to each action with this with confidence as variance. I'm going to sample out of that for each action and go with the max. If I do this with high probability, I'm going to randomize among the good actions that are like I'm confident about the value, and barely I'm going to take the action which is bad. Let's assume there is action. My estimate says the action 6. My estimate says my value is bad. If I do epsilon greedy again, I have same problem. If I do like a Boltzmann exploration, I get same problem. But if I draw sample from the Gaussian distribution, I feed it to the sixth action. What I get, I'm gonna randomize the sixth action more since I have a higher confidence. So how can I get this confidence? How can I approximate this confidence? Is instead of solving this regression problem, I'm gonna solve this Bayesian regression problem. I can fit it with a Gaussian distribution. Why Gaussian? So it's like has nice property, the prior and like likelihood are conjugate. You have a closed form. And like for linear contextual bandit, we know if we feed like a Gaussian to the confidence, we get a sample complexity guarantee. And Yin, I think 2 years ago, had a paper he showed that for the tabular setting, if you do Bayesian linear regression, you get a optimal sample complexity. And there are some hyperparameters. The good thing about this model is like the amount of time I spent on like hyperparameter tuning was like less than a day. There are like 2 sigmas you need to tune for. So it compared against DDQN. So x-axis is time, y is like a return. I'm not comparing numbers, I'm just showing the sample complexity. Since we expect that it gives us a good sample complexity. I like you to pay attention to the last 2 columns. The last one is like how many samples BDQN needs to beat DDQN, and the second last is like how much sample BDQN needs to beat the human score. Thank you. I think there's no time for questions now. I just overtime. Yeah. Thanks.
Next up, we're going to have Ahmed talk about randomized value functions via multiplicative normalizing flows.
Thank you. So my name is Ahmed. I'm presenting randomized value function via multiplicative normalizing flow. It's a joint work with my colleagues Harsh, Joshua, Joelle Pineau, and my supervisor Pascal Vincent from Facebook, AI Research, and Mila. So the aim of this work is to scale up a randomized value function. So randomized value function is a way to do exploration with generalization. So instead of having a point estimate of your Q value, we maintain posterior belief over Q value. So to this purpose, we leverage recent advances in variation Bayesian neural network, and the main idea is combine DQN with multiplicative normalizing flow. Some background for variation neural network. So if you have a network parameterized by W that models the probability of Y condition of X, so variation inference consists in defining an approximate posterior and then maximizing the evidence lower bound, elbow, which is formed by 2 terms. So the first term is so the expected the expectation with respect to the approximate posterior of the log likelihood, and there is the KL divergence between the approximate posterior and the prior, which is the regularization term. So straightforward way is to use the mean field approximation, which assume a fully factorized Gaussian, which is very restrictive approximation, and this can underestimate uncertainty. So we use in this work multiplicative normalizing flow, which is a family of approximate posterior that can introduce arbitrary dependencies between weights. So the idea is instead of sampling directly W, we sample an auxiliary random variable Z from some parameterized distribution, and then we sample the W condition on Z, and this conditional distribution is factorized Gaussian, but the marginal of W is actually an infinite mixture of Gaussian, so we can have arbitrary dependencies between the weights. So the flexibility of the distribution over W relies on the flexibility of Z, and the trick here is that if you use if Z is much lower dimension than the vector W, so we can allow ourselves, for example, to use normalizing flow to modelize the distribution over Z. So normalizing flow is a family of invertible transformation for which we could compute for which the determinant of Jacobian could be computed efficiently. And the idea is we start from a very simple distribution, and then we apply successively multiple invertible transformation. And at the end, we obtain much richer rich distribution and multimodal distribution. So to optimize the elbow, we need to use the parameterization trick. So the idea is to parameterize the random sampling from the distribution over W and Z in terms of noise variables and deterministic function as follows. So we sample a noise from standard Gaussian, and then we apply normalizing flow to obtain ZK. And then once we have ZK, so act multiplicatively on the mean of the distribution of W, and then we sample other noise for W to get the Gaussian distribution of W condition of Z. And that's why it's, the name is multiplicative normalizing flow, because the normalizing flow, which is be considered as variation dropout parameter, act multiplicatively on the mean. So the overall algorithm is basically the same as DQN, but after each update, actually we will sample new noises for W and for Z. And then we obtain a sample from the Q value, and for a few steps, we select action greedily with respect to this Q value, and then we do SGD step for with respect to the objective, which is the elbow. So So the first term, which is the log likelihood, corresponds to the TD error. So it's the usual. Loss of DQN plus regularization term, which is basically actually an upper bound of the KL divergence. And then we resample new noises. So we took, for the experiments, we have 3 baselines, so epsilon greedy, noisy DQN, and baby QN. Okay, so I'm running time. Okay, for the experiments, we can just come to my poster. Thanks.
Let's thank the speaker again. Next up, Christoph is talking about on Oracle efficient. Sorry, Christoph is not talking. Instead, we have.
Hey, I'm Akshay. This is joint work with Chris Dann, Jiang, Alekh Agarwal, John Langford, and Rob Schapire. And actually, we've been trying to resolve Ian's wish list for almost 3 years now, and let me just tell you about a little bit of our progress. So what are we trying to do? We're trying to come up with algorithms that do sophisticated exploration, what Ian's calling deep exploration. They also do generalization, so they're using some sort of function approximation, and they're computationally efficient. So let me start off with kind of a little bit about what we know. So we know that for tabular problems, so if you want to just do computational efficiency and sophisticated exploration, there's lots and lots of algorithms. One of them is E cubed, this Kearns and Singh paper. There's lots of other ones. But when we go into sort of, oh, I see. So, but you know, algorithms that people are using with function approximators, like epsilon greedy, this is what Ian was talking about, you can prove that they'll get exponential sample complexity in even these little baby tabular problems. And of course, what we're trying to go for is algorithms that solve these hard reinforcement learning problems where you have to do function approximation, maybe with a neural network or something, and we don't really have a good answer here. So let me just tell you a little bit about what we're trying. So in 2016, me, Alekh, and John, we did this paper where we're studying these problems where there's a low dimensional latent representation. So think about this little grid world on the left, but the agent is actually seeing this observation from a visual sensor. And let's also imagine for now that the latent dynamics are deterministic. And so here we had an algorithm that runs in the sample complexity, something like polynomial in the number of hidden states, with no dependence on the size of the observation space, which is this rich visual inputs. The downside here is this algorithm is based on enumerating candidate Q functions. And you can imagine that you need a big bag of candidate Q functions if you want to use the observation to learn. And last year with Jiang and Rob Schapire, we sort of extended this result to handle the same environment settings, but with stochastic dynamics. So this is sort of the original problem we tried to solve. It turns out it also solves a much broader class of problems, and at anything that has this sample complexity parameter that we call Bellman rank. And environments like tabular MDPs, low rank MDPs, linear quadratic regulators, all these problems you can prove to have low Bellman rank. Again, the downside here is that these algorithms are based on enumerating a set of candidate Q functions. So these are sort of resolving Ian's first 2 comments. You want provably efficient exploration with generalization. These are both algorithms that do that, but these algorithms are not computationally efficient. And so we've been trying to go after this. And so now we have a new family of algorithms, there's actually several, that work back in the deterministic latent dynamics situation. They still run in polynomial in the number of hidden states, but they are reduced to common algorithmic primitives like linear programming and supervised learning. So these algorithms are computationally efficient, but they only work in a restricted set of environments. And then we also are starting to think about what can we do in the more general case. And we only know this one algorithm, it's called Olive, for the more general situation. And unfortunately, we were able to show that the Olive sort of reduces to an optimization problem. And this optimization problem is NP-hard even in the most basic situations. So there's something still open, and we're looking for help. So if you want to understand more, come and talk to us. Let me just tell you a little bit about what this new algorithm does. This is called Valor. So the situation is you're kind of in a grid world, and, but then the agent is receiving observations from a visual sensor. And when you think about a grid world, and the dynamics are deterministic. So when the agent makes a sequence of actions, it arrives at an underlying hidden state. And the key thing to doing good exploration is to sort of understand if two sets of actions take you to the same hidden state. So if the agent goes, red, red versus green, green, it ends up in the same place, and it should decide to only consider one of these in the future. And this is a way that you can prune what's an exponentially large set of action sequences into just a few ones that are important. And basically, we've come up with a way to do this kind of test using the observations that the agent gets when it rolls into this, when it rolls in on both of these paths. And these tests can be written as linear programming problems. So now the main question is, what if we remove determinism? And yeah, I won't tell you too much about it, but we've proved that this optimization problem that all of this algorithm introduces is NP-hard. This is not a proof that the harder setting is not possible, because this is just it's just something about the hardness of the optimization problem that Olive induces. And getting a good algorithm in the more general setting with maybe stochastic hidden state transitions is still open. And if you want to know more, come talk to me. Thanks. It's probably not enough time for a question.
Okay, so hi everyone. This is joint work with John and Alekh from MSR New York. And so I'll be talking about basically an evaluation of a lot of practical exploration algorithms for the contextual bandit problem. So most of the papers here are about RL. So one way to see contextual bandits is basically it's a one-step RL problem in which maybe you observe a state xt or a context, and then you have to pick an action, and you just see this loss for the action that you actually picked. But you don't have this, so you have an exploration problem because of this bandit feedback. You only see the loss for what you actually decided to do, but you don't have this like multi-step sort of like credit assignment problem. And this is much closer to a lot of real world setting, let's say in online recommendations. So it's an important problem to tackle well. And let's say, basically until now, a lot of the algorithms have been based on theoretical regret bounds, so efficient exploration algorithms that give you like nice guarantees. But there are some issues with a lot of these methods, and one of it is computational efficiency. So in particular, a lot of the algorithms tend to depend on the dimension squared, so it would much be very, very complicated in practice. Some other methods might alleviate the computational problem, but they might have some guarantees that are often too conservative. So like they might work in the most difficult sets of problems, which typically means that you have to do a lot of exploration, and this could be very costly in practical scenarios. And finally, a lot of different methods haven't really been compared too much, so this is one of the things that we try to tackle here. And so I guess practice is what we try to do, and we try to evaluate a lot of these algorithms on a very large class of supervised data sets. We focus on practical methods that rely on these optimization oracles that I'll describe soon from supervised learning. And we have implementations available and some improvement to existing methods, and everything's in this online platform, Wabbit. Just so one slide about optimization oracles. Basically what we try to do here is that when you have some observed data, so some context vectors xt, and then you try to create some virtual like cost vectors ct here, maybe based on like previous observations of rewards and losses. And basically we assume that we have efficient ways to estimate these policies, for instance pi here, that map the context to an action by optimizing this problem. And these are things that we know how to do in supervised learning. And another example is just regression here. So you try to find these functions f that map a context in an action to an observed loss. So maybe yt is just what you've observed in the past. And so typically what you might want to do is here is try to reduce to off-policy learning. And a lot of algorithms work by reducing to this problem. So in terms of algorithms, these are sort of the main algorithms that we consider, and there's some of different families. So there's some like epsilon greedy like baselines. There's some optimism-based methods like this last one here that actually works. All of these work with these oracles that I described before. There's some Thompson sampling approach. There's a more conservative, this cover algorithm or monster paper, which is a little more conservative, but makes a lot fewer assumptions about the distribution of rewards. And the way we evaluate, so we look at all these data sets that I talked about before. And what's interesting is that if you look at the more general supervised problem, like you might have some data sample like xt and maybe a cost vector lt, there's the losses. And this is actually a very general settings that might describe the sampling process in IID contextual bandits. And so the way we simulate the problems in this case is we just let the algorithm pick an action, and we only reveal the loss for the existing action. And once we have two methods, we evaluate them on the data set by looking at some statistical test of their performance on this data set, and then we aggregate things in different ways. So I don't have too much time to go to details, but these are basically some kind of win minus loss numbers on all these data sets. And we see that the optimism strategy is usually dominating most of the data sets. And it turns out that this greedy method, which is actually a very simple baseline that doesn't do any explicit exploration, but only leverages the diversity of the data in some way, is actually very competitive. And the other ones are usually a lot more conservative. And just one little picture here is, here we have this more conservative cover algorithm. It's still a more efficient variant than what's originally proposed. And we can see that greedy typically beats it on a lot of very simple data sets. Whereas cover, so it tends to work better on some, so here, I guess for cover, lower is better. It works better on like some harder problems, but you can see that we would like it to be a lot more efficient in these easy data sets, because otherwise you're just wasting explorations in some sense. So just some conclusion, we've seen that there's some methods like even greedy can actually work very well in some easy data sets because they make strong modeling assumptions. And we have these more sort of robust algorithms that work well in difficult problems, but they're often too conservative, and this raises a lot of theory and practical questions about how can we make exploration more efficient. And please come to our poster. There's more results, design choices, improvement, and some open problems. Thank you.
All right. Good morning, everyone. This is work done with my colleagues at Uber AI Labs. So let's start with a little bit of background. So we currently know of many exploration methods for deep RL, and generally these methods rely on computing some form of intrinsic reward to encourage the agent to explore its environment. And kind of the commonality between these approaches is that usually these intrinsic rewards are computed on a per state basis, and a single agent is usually incentivized to sequentially explore its environment. In this work, we extended an invention from the neuroevolution community called novelty search to do exploration in high dimensional environments. And the key differences here is that instead of computing an intrinsic reward based on a single state, we compute it over an entire episode. And we also use multiple agents to explore the environment concurrently. And so let's overview what novelty search is. What novelty search is an evolutionary algorithm to encourage novel behaviors by ignoring the reward. And so we can see in this maze where the objective-based agent is trying to reach the top right, it fails to do so by achieving a local optima. Novelty search will be encouraged to continually explore different parts of the maze and eventually have a policy that reaches the green dot. So there are three characteristics that define novelty search. The first is a behavior characterization, which has a holistic representation of what an agent's behavior is in this episode. We can consider an example of this to be an agent's XY position in its trajectory. The second is an archive of past behaviors, which we store to compute the novelty of our current policy. The last one is a behavioral distance function, which tells us how close or how far we are from our previous behaviors. And so the natural question becomes now is how can we scale this up to the deep reinforcement learning setting? And so what we do is we rely on a method called evolution strategies, and the intuition here is that we sample locally in parameter space, we compute the reward of our samples, and take a finite difference approximation of the gradient. And so Solomons et al. Showed that this works for deep RL, but there was no previous method to do directed exploration for this task. And so what we do is combine novelty search and ES to do exploration in high-dimensional environments. And our method is pretty simple. So the first step is we sample an agent from a population of M agents. We compute the novelty and reward of this sample, and we take a gradient with respect to a weighted combination of novelty and reward, as expressed by this equation on the top. And finally, once we compute this update, we add the behavior characterization to the archive so that future policies can be novel with respect to this current one. And so we introduced 3 types of methods with varying levels of W, the first being novelty search ES, which only follows novelty steps, a second which trades them off equally, and a third method that's an adaptive method, which starts out following reward initially, and then starts to try out different values of W when it gets stuck. And so we try this on a humanoid locomotion domain, and in this humanoid locomotion domain, the agent is incentivized to go in the direction of the red arrow. But in the direction of the red arrow, there's an enclosure that can prevent it from getting very high rewards. And so what we see is that ES always learns to enter the trap but never learns to avoid it by this flatlining right here. Novelty search learns to actually avoid the trap but is slow to do so, and the reason is it learns to explore in various random directions and not in the direction of the red arrow. And the scatter plot is one evidence for that. Methods that combine novelty and reward learn to achieve high scores by exploring the environment and also learning to do the exploration in the direction of the red arrow. When we scale this up to higher dimensional tasks, we found that the same conclusion applies. The methods that combine novelty and reward perform best, and the adaptive mechanism that trades it off outperforms ES on 9 out of 12 games. And so we can conclude that adaptively adjusting the novelty, preference for novelty and reward throughout learning is often the best strategy. And for a full comparison with other deep RL exploration methods, please see our full paper. And so the conclusions we can draw from this is that novelty is an effective exploration signal in high-dimensional environments, and that population-based exploration is often beneficial. We demonstrate the value of intelligently balancing the preference for novelty and reward over time. And this also raises some interesting possibilities for combining methods from neuroevolution and the traditional deep RL literature. Here we try one example of this with novelty search, but we believe that there are many more. I'd like to thank my collaborators and the audience for their time. For any further questions, please see our poster.